All right, so today we're going to continue reviewing Calc 1, although we're almost done. What we need to do is take a look at some theoretical results known as the first and second fundamental theorems of calculus, and then we're going to reintroduce to ourselves a special technique for finding integrals. And then when all that's done, we can dive into chapter 7, which is our first new chapter of the semester. And that's where we're going to learn about applications of integration. And then, of course, in chapter 8, we'll be looking at a very large number of very advanced integration techniques. Okay, so let's get back to chapter 4. Now, we really only have two more sections left here, 4.4 and 4.5. So here I would like to start by showing you the so-called first fundamental theorem of calculus, because there are two of them. Although they're both basically telling us the same thing in a somewhat different way, they're basically telling us that integration and differentiation are inverses of each other. I mean, that's really the bottom line. So this statement tells me that if I integrate f of x over the interval from a to b, I can actually solve that by taking f. Now remember, f is the antiderivative or integral of lowercase f of x. If I simply evaluate that result at b and then a and subtract one from the other, I'll end up with the same thing as calculating the definite integral. So let's take a look at an example. We'll start with this one, and you'll see how this works. All right, so the first one is from the integral from 1 to 2 of x squared minus 3 dx. All right, so what we're going to do is calculate the integral, but all right, we'll do this right now. First of all, you know that we can break this up into two pieces. Now we can apply the rules that we know, our rule in this case. So we'll have x cubed over 3. Now, because it's a definite integral, we don't need the constant of integration, but instead we need to evaluate it over the interval from 1 to 2. So we'll write it like this. I'm sure that some books might write this slightly differently, but this is a standard way of expressing the idea that we're going to evaluate this function. Now, by the way, notation-wise, this is what we mean by f of x. Okay, so that means when you solve for this, you're plugging in the 2, and then you're doing the same thing for the 1, and you're subtracting 1 from the other. But we can think of this as f of b, where b is equal to 2, and a capital F, I should say. I should be very precise about this. We have to be very careful which F we're talking about. Lowercase f is, of course, the original function. Capital F is what we mean by the antiderivative or integral. So capital F of b is here, and capital F of a is here. Remember, this is a, and this is b. Okay, so that's what we're actually doing with the first integral. So we're not done yet because we still have the second one. We have the integral of 3 dx right here. So that is again integrated between 1 and 2. And you can think of this as f of b and f of a. Now, of course, don't forget, we still have to subtract 1 from the other. I broke it up into two pieces so we could, handle them individually, but don't forget, you still have to come back and recombine them at the end. So you're going to end up with 7/3 minus 3. Of course, now we need a common denominator, and we ultimately end up with minus 2/3. Now, you're probably wondering, how is it possible that this area is negative? Well, let's take a look at this graph in Symbolab. It's a quadratic equation, obviously. All right. X squared minus 3. So we really don't need symbol after this, but let's just go ahead. It's a very simple function. You can tell just by looking at it that it's an upward facing parabola where the intersection is -3. I recall, just as a side note, that when you're illustrating a quadratic function, the coefficient of x squared is what determines whether the parabola faces up or down. So let's say here we have this piece. Um, that indicates that a, whatever it is positive. Here, we know that a is negative. This and the c is the intercept, the vertical intercept, I should say. So because in this case, our graph, our function is x squared -3, we know that the parabola is facing up and the intersection is -3. So I'm going to copy that Symbolab graph, that very beautiful graph, into my document here. Now, if I'm not mistaken, I think on a Mac, you already have the ability to take snapshots of the internet, whatever's on there. I'm not sure if that's true of the PC, but this package that I use, Snagit, does a very nice job, I must say, although I have to pay for it. And what it does is it gives me the ability to copy off the internet. Um, I'm not sure what format it's using, but it seems to work pretty well. All right, so I just want to put this in here so I can write on it. All right, so this is now keep in mind they asked us to integrate between 1 and 2. So 1 would be right about here. All right, well, that's not exactly a straight line. Let me see if I can fix that. So basically, this is what they're looking for. And you can notice the entire area is under the horizontal axis. That's why it turned out to be negative. Okay, so in other words, the area isn't actually negative. But when we have areas underneath the curve, they will be negative based on this rule that we're using to calculate that area. So that's why it ended up being -2/3. So when you see a negative like that, it means it's underneath the horizontal axis. All right. Oh, what about this one? So we have B. Now this one, looks a little messier. It's not too bad. Let's try that one. 1 to 4, 3 radical x. And of course, what we should probably do is simplify just a little. Let me write x as radical x is x to the 1/2 power. And I'm going to evaluate that between the values of 1 and 4. Now, of course, divided by 3 halves is a constant clearly. So what I'm going to do is rewrite that as 3 times 2/3. Just simplify it a little bit. And that means we have 2. And now we can evaluate it. You're going to end up with 2 times x, 4 to the 3/2 power. It's 1 to the 3/2. All right, so now this is a good excuse to remind ourselves what exactly do we mean by raising a value to the 3/2 power. So if we have x to the 3/2 power, which we're essentially doing here, is taking the square root and then cubing it. Okay, so for 4, you're taking the square root of 4 and cubing the result. So that's going to be 8. And of course, 1 is different because any time you take 1 and raise it to an exponent, it's going to wind up as 1. So we don't have to worry about it. And so our final result, when you plug in everything up here, will be 2 times the difference between these two. And it's just 14. Okay. So whatever this function is, 3 radical x. Actually, 3 radical x, the function radical x looks like this. It starts at the origin and it increases at a decreasing rate. So you multiply that by 3, you're just making it steeper. Okay. So it's going to look something like this. All right. Well, it's supposed to be curved. Let me try that again. That's kind of, let's make that, sorry, that's not too bad. So in other words, it's the same thing except multiplied by 3. And so what we're aiming for area between 1 and 4. Just solve that equal 14. All right, and again, all of this is based, as we saw in the first version of the fundamental theorem of calculus. This is not we're going to use most often by a long shot. There's a second one, which is a little more theoretical, that essentially means the same thing, but we'll get to that in a bit. And then the third example that we want to look at is, now all of a sudden trig gets involved. So I don't know about you, but I don't have all of the trig triggers memorized. I mean, I know most of it, but we'll probably have to consult with a table or a calculator. Now, I did find a table here somewhere. This is actually in the back of our book. Here it is. And so if you're ever stuck, you can go look back here, or else you can just go to the internet anywhere, just type in, integral secant squared x. It should come up with the right answer. And so if you look, and you can see there's a lot of them. This is why chapter 8 is so long, because we're going to learn most of these techniques. Maybe not every single one of them, but oh, it just goes on and on and on. Look at this. But anyway, if you scroll down, like, yeah, here it is. No, not that one. Yes, that is what we were looking for. So they're using u for these to keep it more general. You can just replace the u with x if you need to. And then, of course, du is just dx, which is 1. And so if you look here, here it is. It was right here. Okay. So secant squared u du is tan u plus c. If u is x, then it reduces to tangent x plus c. All right, so let's keep that in mind. So now what we're looking for is the integral from 0 to pi over 4, radians, that is. Okay. So yeah, that's all there is to it. And so therefore, what we have is so now we can go look these up in our calculators, or can use, I guess Symbolab can do this. I think it's quicker for something this straightforward. I think it's easier to just go right to your calculator. Just make sure you're in the radians mode. Okay, that would be bad if you forget about that But all right, so remember how this works. The mode button is in the extreme upper left-hand corner. Now, of course, it is backwards, yes, but there it is in the right there. And if you hit the mode, float down, scroll down, and you'll see that the fourth set of options is radian versus degrees. Make sure it's set at radians. If it's not, scroll over there with your arrow key and hit enter. Make sure that that radian is highlighted. Then you go to tangent. And on this TI-84, at least, you're going to type second, and then you're going to have the exponentiation button. This is the symbol caret, by the way. You see this used in many calculators and in Excel and in some programming languages to represent exponentiation. And then that will give you the pi. You can see it there. And then you divide by 4, of course. Close your parentheses and then hit enter. And it just so happens to be 1. What do you know? Now you do the same thing with 0. Oh, what am I doing? No, you just type 0. Okay. Tangent 0 is 0. What do you know? Okay, so the difference between the two is just 1. And you're all set. So again, all 3 of these are examples of the first fundamental theorem of calculus. And the results, and the process we're using here is called definite integration. We're looking for a specific constant rather than a function. All right. Now, the mean value theorem, remember, this came up very early in Calc 1. Here it's being used for a very specific application. It turns out that if you're taking the area under a curve, you can use the mean value theorem to find the average value of the function over that interval. It's a very straightforward process. In fact, it is right here. Okay, so let's do some examples of this. So you can easily imagine applications for this, like in economics, you might be asked to say, well, I know that the cost of producing my product can vary depending on the quantity. On average, how much does it cost me to make this product that I'm producing? I need to know that, obviously, to survive in business. If I don't know what my own costs are, I'm not going to hang around very long. Okay, so here it is. And so the example they're going to give us is, actually here they're going through improving y. But right now, let's just focus on this example. The function is 3x squared minus 2x. And in a second, we'll go see what that looks like in Symbolab. And then the interval is 1, 4. All right. So 3x squared minus 2x. Here it is. That's so much stuff open. Just double check. 3x squared minus 2x. Beautiful. You notice here that it's a nice looking graph, but 4 is way out here somewhere. So in other words, the value of this function when x equals 4 must be quite large. So I guess we could zoom in on it. Yeah, oh my God. So it's going to be up in this neighborhood somewhere. But the key is that it is going to cut through the origin, and then the curve rises at an accelerating rate, and this is what it looks like. So what they're telling us is that the average value during that interval is, remember, A is 1, B is 4. All right. So of course we'll simplify this whenever possible. So we have the first one can be written like this. And then we can actually evaluate them. Don't forget about the 1/3 on the outside, though. All right, and we can still simplify just a little bit more. And 1/3 is just simply x cubed. And here we simply have x. All right, so let's evaluate these using, of course, the fundamental theorem of calculus. First case, we have a 4 cubed minus 1 cubed. In the second case, we have 4 squared minus 1 squared. 64 minus 1 minus 16 minus 1. So yes, we have to be extremely careful here with all of the negatives floating around. And there we go, 16. Okay. So, and then in the graph in the slides, they're showing us that yes, it is 16. And so that's our average value. Now, here's a second fundamental. Now, this one is a little bit more involved because what they're saying is, well, if you're integrating not between two constants, but if you're using a function for the upper limit, that changes it a little bit because what that means is that you're solving not for a specific constant, but you're solving for a function. Now, there's a function that can tell you how much this area will be given the value of x. Okay, so it's like an all-purpose function that will give us the results to no matter where the x happens to be. Now, notation-wise, we have to be very careful here because if you notice, they've all of a sudden sneak t's into this expression. These t's are often known as dummy variables. They're there to avoid confusing us. In other words, we know this approach. So here you're solving for a specific value, and over here, instead, we're looking for a function. Because we're really doing two things at once with x. We're treating it as the variable that's being integrated, but we're also using it to define the endpoint. So in order to avoid any confusion, we're going to routinely do this. You'll always see this in all calc books. We're going to change the function variable to something else. It could be any other letter in the alphabet. So how exactly does this work? Let's see. Here's an example. Cosine t. So let's say we're interested in integrating the cosine over any interval from 0 to x. X could be literally any real number. Now, just as a reminder, the derivative of the sine is the cosine, which means the integral of the cosine must be the sine. Okay? But because this is considered to be a definite integral, we do not need the constant of integration. The rules are exactly the same as what we used before with the first fundamental theorem of calculus. And so we end up with, and if you go to your calculator real fast, you'll see that in case you've forgotten, or you don't happen to have a little table right in front of you, the sine of 0 is just 0. Okay. All right, so let's see if they've got a graph of this. They do. All right. So the cosine, if you remember how that works, it's a. Let me go back to symbol lab real fast. The trig functions are not usually very straightforward to graph because they repeat themselves many times. So we'll start by just getting the graph of cosine x. Just a quick reminder, um, peaks and valleys. Yeah, I mean, it's simple. So in other words, the cosines. Well, you see, now here's the thing. They're not actually giving us a specific upper limit. So the starting point is 0, but end up literally anywhere along here. This point, so they usually identify these points limits. Um, okay, I just want to make sure I didn't forget this. It cuts to that axis at 90 degrees, which is pi over 2. Okay, so if we drew this thing ourselves, this is what we're looking at. Okay, suppose that they chose the upper limit to be, in fact, pi over 2. Um, that would be this last case. And you want to know, well, what is that area? Well, according to this theorem, so in other words, it's going to be sine of pi over 2, which is, 1 second, I think it's 1, but I just want to make sure. It is indeed 1. All right. So I could now choose any value I want. For example, what if I'm only interested in finding the value of this area under this curve up to pi over 4? All I would need to do is solve with pi over 4, which is sine pi over 4. All right, let's see what that is. It looks like it's radical 2 over 2, approximately 0.7. So they've gone ahead and done some of these for us. So, you get the idea. And then what they're basically telling us is that, like you would expect, if I differentiate this expression with respect to x, it'll just bring me back to the original function because, again, integration and differentiation are inverses of each other. So if they asked you a question like this one, and you notice the t's are in there, the dummy variables, um, the different derivative of that is simply this function, except evaluated at x. Net change theorem. Now, this is interesting. This is a physics application, although I suppose it could be used for other areas like economics. Um, Now, f prime, remember when you see a little prime, it means you're taking the derivative of something. So what they're saying is that according to this theorem, if we define f prime of x as the rate of change of a variable, not the actual value at a given point, but the rate of change, and we can solve as f of b minus f of a. Okay. So the example they're going to give us is liquid filling into a tank. What a classic physics example this is. Something is filling into a tank. All right. And they're giving us the speed at which we're filling this thing up. So here's our tank. The liquid is gushing into the tank. Okay. Um, it could be filling over a bathtub, for example. Um, and so, but they have to give us now, this is the rate of change. Okay. That's the important thing. So they're going to define C of T is the level or the amount of this water, let's say, or liquid that's in there at any given time. Of course, when you're dealing with time, it's understood that t equals zero usually is right now at this point in time. And then after that, it depends on the problem. It could be 20 minutes in the future, or 20 hours. It depends on how the problem is set up. So then that implies that C prime of t is the rate of change of t, of C rather, with respect to t. There's how fast is it filling in? Now they're telling us not C of t, but C prime of t. This is actually C prime of t because it's the rate at which the magic word there is rate, 180 plus 3t. So, and by the way, the fact that it's written like this, at time, well, all right, well, we'll interpret it later on. Let's just take care of this now. So what they want to know is this is only defined over the interval from 0 to 60. I guess when we get past that point, we turn the water off. Okay. They want to know how much water is in the tank after 20 minutes. So here's what you're going to do. You're going to integrate from 0 to 20. Remember, according to the second fundamental theorem of calculus, that means all we have to do is integrate 180 plus 3t, and then evaluate it over the interval from 0 to 20. In other words, this function in here is C prime of t Think of this as f of 20 and f of 0. In other words, the integral of value at those two endpoints. So what we have here, 20 times 180 is 3,600. Um, this is 20 squared is 400, 600. 4,200. So they're claiming that after 20 minutes, there should be 4,200 gallons, I guess, of the liquid. Liters. Okay. So this is what they're giving us. Now, what you could have done, I mean, the other way to think about it this is that if C prime of t is 180 plus 3t, C of t is, as you saw, for guns. It gets a little carried away like this sometimes. It depends on where my hand lands on this tablet surface. I've got this enormous tablet here that I'm writing on, and it can have its moments. So we integrated this thing. We discovered that the integral is 180t 3t squared over 2. So in other words, you're evaluating the actual function that tells you how much liquid is in the tank at any given time. That's, I mean, essentially that's what you're doing. And so that is going to give us, what do you know, 4,200. So the second fundamental theorem of calculus is what justifies our ability to do this. Okay, because as it's trying to explain to us that integration and differentiation are inverses of each other. So we can go about this in a couple of different ways. Now, there's some other examples in here with particles and stuff, so I think maybe skip over that. But what we would like to do is move on to the last section of our review, which is 4.5, because this is where we're going to reintroduce one of our old favorite rules, if you remember from Calc 1. This is really one of the only rules that you were given in Calc 1 about integration, and that is integration by substitution, or sometimes it's known as U substitution. Okay, so this is an important one because you run into it quite often, especially when you're integrating polynomials, but it's not restricted to polynomials. How does this work again? So let's jump through the theory a little bit. Just be aware that what you're effectively doing here is you're dealing with functions that themselves involve the chain meaning, and that's because they're composite functions. So in other words, when you integrate here, what you're basically integrating is a composite function. So that will affect the way we go about finding the correct answer. Okay, so in other words, you're taking the integral of a composite function. So in effect, you're reversing the chain when you do this. So here's a classic example of this. And they're trying to help you here. They're going to help us set up these little categories. Eventually, we'll put together a little table to help us remind ourselves how many different techniques we know and when to use them. But ultimately, a lot of this just comes down to practice. If you practice often enough with these techniques, you'll get to the point where you recognize right away which one is the most appropriate, because that's really half the battle with integration. We have so many possibilities to choose from that you say to yourself, well, which one should we use? Well, sometimes it's not that clear. All right, it does come down to practice. So let's try this one. And again, like I pointed out, this one is integral of a polynomial, but there's a product involved here. So that's going to make things a little bit more complicated. All right, let me just quickly write this down. All right, so again, we have x squared plus 1 squared. Oops. Okay, so it looks on the surface, if you've completely forgotten about u substitution, this one might look really terrifying at first glance. Okay, but it's not. Hold on, let me see. I think we're done with this one. Let me just get it out of there. There we go. X squared plus 1 squared, 2x dx. So what exactly are we trying to do here? Well, we're going to pick some part of this expression and define it as u. Usually that will prove to be the most, let's say, complex part of this expression. So for example, here, why don't we start with x squared plus 1? How does that help? Well, let's take a look. This implies that du dx is 2x, which in turn means that du equals 2x dx. So those definitions, I can rewrite this as u squared. And, oh, this is just du. Now look how easy this is. It's a simple case of a variable raised to an exponent. We know how to deal with these. So it's going to give me u cubed over 3 plus c. And now the only remaining step is to substitute the definition of u. Yeah. Now, by the way, as always, when you integrate, if you're not sure you've done this correctly, you can just double check by taking the derivative and seeing if it brings you back to this original expression. Um, so here, for example, you recognize right away that you need to use the chain rule for this one. You don't need to bother with the c because that derivative is just 3, 0 rather, sorry, it's 3, it's 0, but here in the first case we have x squared plus 1 cubed over 3. So I can actually bring this 1/3 outside if I want. So based on the chain rule, this is what I'll end up with. Okay, so that leaves me with, now the threes cancel each other out. That's of course where we started out. Okay, so that means we must have done this correctly. So all u substitution basically follows the same logic. Now, having said that, it's easy to make mistakes. So if you started out choosing the wrong thing for u substitution, you'll find that you're not getting anywhere. You're making a mess, basically. Then you can go back and try something else. Now, it's possible too that u substitution is not going to work on a particular example. It's not for every integral. In other words, it's only works for certain cases. Those cases are the ones where the chain rule was involved in the original function. So if you can't seem to get to the end with the u substitution, it means you may have chosen the wrong technique. Or if you can't seem to get to the right answer, you might have simply chosen the wrong u. But that's easy to fix. Just try something different. But always be aware that the u will often be the most complicated part of the original integral. All right. Well, I think they have some more examples waiting for us. Let's try. Yeah. So here they're reinforcing the idea that you're basically integrating the result of taking the chain. Okay. Well, they've got plenty of examples for us. So we don't have to do every single one of them, but let's just get a few under our belts. It's all good practice. We'll start here. So again, if you notice, you've got a fairly complicated expression. In other words, this expression x squared plus 1 has the highest, it's a second degree polynomial. And so why don't we start with that? And if it doesn't work, we'll try something else. Now, everything looks good. The only problem is you've got your 2x here, your x here. It doesn't matter. You can just rearrange it. And now you can see that you've actually got your u to the fourth u. Oh my God, it couldn't be any easier. That's it, you're done. Wow. So you can double check if you want, but it's you don't have to do it for every single one. Just if you're really not sure, if you just want some practice, it's double checking is it's really up to you, but that's how you would do it. All right. Um, I'll tell you what, let's jump into this one. Ooh, that looks tricky. Oh, what do we do now? Now remember, we need du. So if you remember, somewhere along the way, we reminded ourselves that the derivative of the tangent is secant squared of x. So let's see if we can find. Oh, okay. Yeah. According to this tiny, tiny little chart here, the derivative of the tangent is in fact the secant. So let's try this. So I don't have to worry about the three. The derivative is just zero, and that means that du secant squared x. And again, I mean, we may have to change the ordering of these terms a little bit. No, so this is our u. This is our du. Oh, so easy. And that's it. We're done. All right. So even though there's trigonometry involved, it turned out not to be a terrible difficult problem. But again, if you didn't remember that the derivative of the tangent is the secant square, you were not going to get the right answer. All right. Now there's a couple more down here. Now these are here. They look like they're awfully similar. There's a reason for that. Let me just show you this one real fast. There's a reason why they brought these up. You might say, well, we've already done a few of these. Why do we need to keep practicing? Well, we're going to run into a bit of a problem with this one. And if you rewrite this, you're going to see what the problem is. Don't have dx. We have x dx. We don't have 2x dx. What do we do now? Oh, no. Well, because the problem here is that there's a constant missing, we can actually create it ourselves. Okay. Watch what we're going to do. So if you can tell, see, I mean, I've just multiplied the entire expression by a half and by 2, which means I haven't changed anything. But now all of a sudden, I have what I'm looking for because this is my du. So when you have your du, almost, not quite, but you're missing a constant, you can supply it yourself by the appropriate multiplication and division that will turn whatever you have into some function of u times du. So in other words, this way, the process is very, very flexible. So, you don't give up, you don't try a different U. You see if you can supply a missing constant. Now, if that doesn't help, if you're missing like an X or something, that's completely different. You can't just throw that in there. But if you're only off by a constant, it's an easy fix. All right, and so this time, remember the U is the X squared plus 1. Oh, whoops, sorry. I'm sorry. I just realized I copied it wrong. This is 4. Oh, after all that work, you don't want to make a mistake on something silly like that. Yeah, the exponent was 4, so that means this is 5. It's so easy to make, this is why this stuff can get so frustrating, because you can have these great ideas and make the dumbest of mistakes along the way. All right, let's try it again. Right now we're talking and we're good. All right, that's good. And you know what? I'll tell you what, in this case, why don't we go ahead and differentiate it? And we can move the 1/10 down here. By the chain rule. Okay, so let's gather up some of these terms. We have 1/10, 5. And so we end up with x times x plus squared plus 1 to the 4th. Okay. In other words, I've got a 10 here and I've got a 10 here, so it's just x squared plus 1 to the 4th. And in fact, this is what we started out with. So we must have done it correctly. All right. Now, we're running out of time for this session, but let's see what's coming next. We're so close to being done the reviewing. We still want to look at, well, they're introducing the so-called the general power rule. Um, Change of variables. See, now it's getting a little bit more involved. So we'll save this for the next time. Right now, though, we're in pretty good shape. We're very close to the end. And when this is done, the next session, I'm pretty sure we'll spill over into chapter 7. We'll lay the background for that. But here we're getting very close, but there's some more results that we need to be aware of. And so we'll save those for next time. All right, I'll see you then.